Okay, you know what I just realized? We don't have a note well on the chair slides. So I'm just gonna put, no, that's okay, I'll put from my other session.
Okay. Edit the slide deck and put it in then.
Yeah.
Okay. Okay, now that we have a whole bunch of more potential volunteers in the room, we cannot begin until we have a note taker and a jabber scribe. Any volunteers? Thank you. Still need a note taker, a minute taker. It's a strong message to the area director that we didn't have enough energy to take minutes.
I'm allowed to note taking. Thank you, Bob. I will contribute to the note taking. I'm already underneath the bat.
Thank you.
I'll do the best I can. I sure hope somebody else gets on it.
Somebody else help Bob, please. Thank you. All right. So Brian Rosen agreed to do the jabber scribe. Bob Moskowitz and Alex agreed to do the note taking inside the Etherpad. Thank you. So call your attention to the note well that's on the screen. At this point in the week, you've seen it a whole bunch of times, but still take note of what a contribution is to the IETF. Next slide. So the first thing we're going to talk about is the charter. At the URL on the screen, we have the draft text for the charter. It's been stable all except for 2 sentences for a very long time. Those 2 sentences since Monday. I have not seen any discussion on the mail list since those 2 sentences were changed on Monday. So the first question is, does anyone have any additional issues with the text that's on the wiki? No, I'll get to that. Not yet. Okay, I'm not hearing any new issues, so go ahead.
Sorry.
I'm sorry.
I haven't sent anything to mailing list. I'm a little late to the party. I just joined the mailing list. I did read the charter. I don't know if now's the time to talk about it, but one of the things that last time I looked at the charter anyway, something that seemed to be missing was any mention of the VitaX work that's going on in 3GPP. And by that, I mean simply that, not that we have to work on all the details, but it would be nice that anything that we consider to be kind of higher layer, like IP and above, it would be nice that it's not specific to 802.11p, but that we try to do it in such a way that it works across these different expected error interfaces.
And name, please, for the record.
Vincent Park.
Suresh Krishnan, AD Hat. So thanks, Vince. So the stuff is like, I specifically asked the chairs to stick to a very tight charter because we don't want to do everything in the world, right? So if there is some technology work that we need to be doing, it's certainly okay to discuss it, but it doesn't have to be charted in the first stage of the working group, okay? But if you want something and there's like something ready to go, yeah, feel free to propose it.
Bob Moskowitz, HG Consulting. Further, I'd say that the work in IEEE 802.11p and 1609 is well-defined and something we can work with, whereas 3GPP is still working out what they're going to do in V2X, and we need them to get further along their curve before we can see what we're going to be doing in that arena. We should watch it, but I don't think it's ready for us to start hanging some work on.
So I think the last two speakers have said, let's recharter if something becomes relevant. Are you satisfied that you've been heard and satisfied with that outcome?
Vince Park again. I certainly feel heard, so
Okay.
that's good.
Step one.
Yeah. As far as recharting goes, I guess it depends on, what kind of time frame you're thinking that could potentially be applicable. Because in 3GPP, there are already, TRs that are just about done and a TS that's already in work. So things are happening fairly quick, and they're building on top of the LTD specifications or ProSay specifications, which are already complete. And again, so I don't expect it to be, a drastic, long, drawn-out kind of effort to get that defined in 3GPP for V2X. The other thing there is simply that my understanding of what's going on in 3GPP right now is that they are trying to define the air interface such that much of the wave stack would run over top of it. So again, the idea is to make the link layer somewhat agnostic to what's above it, such that you can reuse a lot of the work that's been done in 1609. And again, it would be a shame if the work done in here did not have that same level of flexibility.
Suresh Krishnan, thanks, Vince. So there's really no time frame specifically involved in the rechartering. So as long as the working group finishes this deliverable, you can recharter. So if it's in 3 months, yeah, sure. Okay.
Tom Harris, Eurocom speaking. When you mentioned that, okay, I agree with the fact that we have to have independence, link layer technologies, LTE, D2D, and everything else. But the standardization in LTE, D2D, now the standard is done, but before it can be deployed, we may have multiple years of testing, which...
Could you speak towards the microphone?
Oh, sorry. Multiple years of testing and specifications. This has been already done for the basically the DSRC technology in US and in Europe at the G5. They are deployed. So that's why basically this is, if we have to do something now with IPv6, this is the technology.
Suresh, do you have any guidance to the group?
Yeah, Suresh Krishnan. So if you look at the chair slides, right? So if you look at the penultimate point, it says for the IESG to approve the charter, right? So just once we figure out who's the constituency for this work, we can narrow down the work, right? So at this point, there's people who said 802.11p is interested in getting this kind of V6 mapping on top. So if there's other people interested in doing the stuff, they come here and sign up to do the work. That's all good. But this is what we heard, and that's why things are written like this today, right? But if other people show up, yeah, for sure.
Another way of looking at it also, Suresh, or an additional point is that that's incentive to actually do the focus work quickly, right? And if there's additional thing, let's get this done first.
Yeah. Can we see the charter, please?
And it's on the link on the slides that are posted, so anyone can also look at it locally with better font size.
Okay, does anyone want to raise anything at this point?
I'm generally pretty happy with what's been said, but I have a question.
Okay.
So let's say let's say it gets formed and within the next month or two, we start to see things progressing on the LTE side. Is it appropriate in the discussions of what's currently in the charter to point out things that are potentially not so flexible or problematic, or that would be better to be done in a more generic way such that it can be extensible to other link layers? Is that
That's totally fine.
okay?
People like code reuse, period.
Dan Romashkano, very, very nitty thing, and I apologize for it. But .11p is now incorporated into the .11 edition, and this needs to be mentioned some places.
Yes, we're aware of that. I didn't want to do a change at this point, but we can do a global search and destroy over P versus OCB.
I posted that to the list, so
Yeah.
that information is now in the email on the list specifically saying that.
In fact, I think you'll see all the drafts talk about that we're going to talk about later if we get past the charter. Okay, could you go to the next slide? I'm going to go. Okay, I'm just moving to the pink box so that I can see the hands that are going to get raised as we go down here. So, assuming the ISG does.
I'm
Yes?
sorry, again, to be a problem maker. We didn't see the work. I think we saw the main beginning of the charter,
He scrolled it.
the standard track document description. I didn't see it in the charter.
Okay, Bassett, the link is posted on the slides, okay? No, on the meeting materials, there's like a link with the charter. It's been posted to the list for like a really long time, right? And there's, but go to the slides, click on it, like, and if you have any questions, bring it back when Russ is like open for questions. Thanks.
Okay, so assuming the ISG approves this charter, I'd like you to raise your hand if you're willing to help write the standards track document in the charter. Thank you. If you're willing to review that document, which should at least include all the people who are helping write it. Okay, thank you. And if you're planning to implement the spec, see Bob, I did change it, of IPv6 over 802.11 OCB. Okay,
Okay, Russ,
I'll read out the numbers at the end.
Okay, so I just want to add like one more thing here.
Mhm.
So specifically to this point, like, is there anybody in this room who either works for a vehicle manufacturer or some kind of component manufacturer for a vehicle manufacturer? That would be good to know, like not just for this question, but it's something that we want to find out for the constituency. Okay.
So what I think Suresh is asking, of those people, of those 14 people who just raised their hand, are any of you working for a vehicle manufacturer or someone who supplies components to a vehicle manufacturer? Sure.
Just wanted to know if you're asking of people that asked, the subset of people that asked to help review? that
No, the
volunteered-
subset of the people who said they would implement.
Okay.
I have connections to a number of those people.
Yeah, we want to know how many of them are coming here.
That's the problem, how to get them to come here.
Mhm.
Maybe I can work on that. I don't know if I can do for Seoul, but definitely for
It's good if vehicle manufacturers come to the meeting, but it should be noted that many people who are not employed by these vehicle manufacturers do work in collaboration. There are many kinds of collaborative projects and bilateral cooperations with specific vehicle manufacturers and who are willing or have already implemented IPv6 over 802.11c. You'll see in the later presentation.
Thank you, Alex. So my point was like, they need to somehow speak up. So they don't have to come to the meeting, but if Bob, you can get them to send an email or something, that would really help build a case like to get this thing approved, right? Like, because what like I'm looking for, okay, is somebody who'll take this work. So we don't want to do work for like nobody to consume, right? So the point is to figure out like, if there's like one person who's saying, I'm going to implement this and like ship it off, right? Like that's good enough, right? But we want somebody who's doing that. We want to find out if there's like one person or one constituent in that thing, in that space. That's it.
Get me the charter, I'll shake the tree.
Thank you.
So, this is Dapeng Liu. Yeah, just a quick response to who is from the vendor side. So I work for Alibaba Group. So we also have automobile business. So we just released our first, we call that internet car this year. So we cooperate with car vendors. So we are interested in this technology. So we are do the experiment with new technology like this.
So that means you should raise your hand. Okay. Well, so we're going to try it again. There seems to be enough confusion. Of the people who said they were going to implement, how many of you are in some way associated with a vehicle manufacturer or someone who sells parts to a vehicle manufacturer? Thank you. All right. Next question. There's 2 informational documents in the charter. How many people are willing to help write at least one of them? Thank you. And how many people are willing to review at least one of those informational documents? Thank you. All right, so to read out the numbers. The first one, willing to help write the standards track document, 15 people raise their hand. Willing to review the standards track document, 31 raised their hand, and I didn't raise my hand, but I will. And 14 people said they were willing to or plan to implement. 6 of those are of the category that they're with vehicle manufacturers or supply parts to them. The informational documents, 12 people said they were willing to write and 28 said they were willing to review. So I think that's a significant show of support that we will share with the ISG. Thank you.
And with that, the first presentation.
Okay, so this is a very simple tutorial about the H02.11p or OCB. As you know, this is a joint work with John Kenny, who is work for Toyota. Thank you. Information Technology Center, but unfortunately he's not here, so I will present the work. So some background about the terminology. So ITS, so what is ITS? Basically, it means Intelligent Transportation System, and there is a link from the US Department of Transportation about the architecture of ITS. And another terminology that used a lot in this group is DSRC. It's called Dedicated Short Range Communication. Another terminology is WAVE. So the full name is wireless access in vehicular environment. So those kind of terminologies, used a lot in this group, and I will introduce in a little bit in the later slides. And the goal of all these technologies, for example, DSRC and WAVE, is to there are two main scenarios for those technology. One is vehicle-to-vehicle communication. The other one is vehicle-to infrastructure, which called V2I, and the earlier case called V2V. And the applications, there are many potential applications. And the most important one is for the safety application. For example, the collision avoidance. And there are other, use cases also available to use these technologies. And how does this work? So this is very high level, explanation about how this technology can work. So each vehicle will broadcast its core state information in a message called basic safety message. Normally will 10 times per second. And the basic safety message is sent 360 degrees using a technology we call that IEEE 802.11p. So I will talk about later in this slide, because the following solution draft is mainly talking about how IP can run on top of IEEE 802.11p. And the receivers build models of each neighbor's vehicles and access that to the host vehicle and warn drivers or take control if threat become accurate. So here is one example. It's about the forward collection warning. So if a vehicle stopped in the road and the other one approaching doesn't stop, so there will be a warning issued within the car. That's one very typical use case. The other use case is we call that emergency electronic braking lights. So in this scenario, if there is a vehicle have a very high deceleration, and for example by traffic jamming, and the other tailing cars will informed by DSRC within 100 milliseconds. And the other use case is that blind spot warning. So the driver receive warning when showing intent to change lines, for example, as this figure shows. And another is that for the normal driving, there is an advisory indicator of car in blind spot. Next use case is the do not pass or warning. So when showing there is an intent to move to an ongoing line, so the driver will receive warning if it's not safe to pass. For example, in this scenario, there is ongoing vehicle and there's another vehicle want to change line. So he will receive the warning message. The other one is the intersection collection warning. So in this case, if intersecting trajectories are indicated, the driver also will be warned. And here is the protocol stack overview of the DSRC or VO protocol stack. So in the physical and the mic layer, IEEE 802.11p will be used. And there is upper mic layer that has the functionality of, for example, multi-channel management, etc. And there are two different protocol stack. The left one is safety message protocol stack, which called Wave Short Message Protocol. So that is used for the safety messages. The other one is for non-safety applications. In this protocol stack, IPv6 and the TCP UDP could be used. And before I go to the slides about IEEE 802.11p, I will introduce a little bit about what is H2.11 BSS, because essentially 11P has another name, which is in the latest version of the IEEE H2.11 standard is called out of BSS. So before we understand what is out of BSS, we should know what is BSS. So it's very simple concept. So the BSS is a basic service set. It's a group of IEEE.11 stations anchored by an access point and configured to communicate with each other over the air link. So the users will use SSID to select different BSS. And for the network, it will use another BSS ID to identify, the BSS. Another BSS special case is in infrastructure BSS, which is we normally called ad hoc mode. So the H2.11p also have a name called out of BSS mode. So there is a flag in the management base. So if this flag is enabled, so the access point, the station will become the OCB mode. So in this mode, the sending station will set the BSSID field to a wildcard value. So in that case, the station can communicate directly over the wireless link. They will avoid the latency associated with establishing a BSS. You don't need to scan a channel and to join a BSS to do the authentication. And so there is no .11 authentication association procedures needed. So that will the security mechanism authentication service will be provided by the app layer or the application layers. So this is very useful for to work in the rapidly varying communication environment. This will reduce the latency significantly. Okay, so that's the presentation. Any comments, questions?
Thank you. So what follows is a block of presentations on 802.11 OCB.
Hello, this is Alex Petrescu. I'm going to present the results of 2 drafts. I would like to say from the beginning that this is ongoing work. We have started this work a few months ago, and several people submitted 2 or 3 drafts, and I'm going to present only what's happening in those 2 drafts. My co-authors are Thierry Ernst and Jong-Hyuk Lee. But I have done this work only thanks to much data that has been provided by implementers and people who prototype this in demonstrators of various vehicle networks, or even you'll see IPv6 in vehicular networks. Okay, their names are Albin Severinson, Marius Makassikis, Michel Vetterwald, Dick Roy, Robert Moskowitz, Alexei Voronov, and Jose Santa Lozano. Also Stark J on itsforge.net, which is a site that I advise all implementers in this space to go consult and find open source that you could play with. So now going back to documents, what is an IPv6 over foo document at IETF? This is a set of questions that needs to answer any IPv6 over foo document that deserves this name. Okay. First, it should decide about its title, and we already had some debate about the title. I will have the question about this later. Then it should specify the MTU, the size of the MTU. MTU stands for maximum transmission unit. Okay, so since this is happening between the IPv6 layer and the MAC layer, this interface should tell to the IPv6 layer how many bytes can it send at once without fragmenting. So this is basically the MTU size question. And you will see we are all used with a classical MTU on Ethernet or Wi-Fi, but you will see that on 802.11p, the answer is not that straightforward. And then how to communicate this MTU between various OCB nodes. This is an easy to answer question. And then who is going to fragment? This is fundamental question, and people make assumptions about it, even though they don't put it in IPv6 over foo documents. But it's always good to know who fragments, IP or MAC, or somebody even below or somebody above. But it's good to know what happens when overpassing this threshold of the MTU size. Then comes the question of the frame format. What is the frame that is carrying an IPv6 packet? What are the headers preceding the IPv6 packet? For example, what is the ether type that we put on OCB, and so on. The first question is easy to say, but the second is easy in general on Ethernet, but it's not easy on OCB or UOC. How to build the interface ID? A whole lot of discussion about it on 6man recently, mainly due to the privacy worries. And address mappings, how to map certain unicast and multicast addresses between IP and unicast or multicast addresses in the MAC. This is the mapping question. So this is the plan, the table of contents we have for our draft, and we have provided some answers to them. But to them, we still have questions, and we would like to have a working group to ask them these questions, to give us advice, to have a common interoperable solution. Okay, it's not sufficient for me or a colleague to write the implementation, but we need to use the same ether type, otherwise it's non-interoperable. So the title, these are the three titles we came with. Transmission of IPv6 packets over 802.11 networks outside the context of a basic service set. Second is transmission of IPv6 packets over the IEEE 802.11p OCB mode, and transmission of IPv6 packets over 802.11 OCB networks. And as you can see, there are some differences between them, but we would like to make a selection. And currently we go with this third one. But if there are any comments, we take the comments, especially with respect to the word networks. I'm not sure whether this is the, yeah.
Suresh Krishnan, AD hat off. I'm trying to figure out, so other than the frame format, is there another difference that you anticipate between, let's say, the last two?
So between?
The last two, right? Like, other than the frame format, what do you see as the difference between them?
There is no actually, the two are just the question of the title.
Okay.
The two are the same.
Okay.
802.11 OCB, and they have the same comment, the same content.
Right. Okay.
So Suresh, sorry. What happened is 802.11p was published, and then when they did a maintenance release of 802.11, they took all the things that had been written since the last one, folded it in, so now they needed a name within the base document, since they couldn't point to the document number anymore, and they named P OCB.
Okay, so, but reading the documents itself, it talks about like one based on Ethernet, another one not based on Ethernet, right? So I just want to understand, because the other one is called OCB mode in one of the three drafts, right? I'm just trying to figure out, is there a non-Ethernet framing format for this?
Yes, for both.
So that is my question. So other than the frame format, what's the difference between one that's Ethernet framing and non-Ethernet framing? So the address mapping, the multicast stuff, and the IID formation, can they all stay the same?
Could always be the same, but we need to refer to some document, okay? And if we refer to RFC 2464, which is the Ethernet document, then many of the recent interface ID configurations are not part of it.
Yes, correct.
So I suppose we would take these new interface ID generation methods from Sixman and at least mention them here.
Okay.
This is the difference with Ethernet. Yeah, this is one difference.
Thanks.
Yeah.
Bob Moskowitz, fun comment on the last two points. As you know, Dick and I have been at it on the list about it.
Yeah.
And I would tend to lean more toward OCB mode over OCB networks, simply because we're talking about the OCB mode function. Is a network or not? We don't care. We care that this is a particular mode of operation of the radio, of the PHY and MAC, and that's what we're taking advantage of. So let's just dodge the whole debate.
Yeah.
And eliminate the meta question at all.
Yeah.
And just say mode.
Okay, noted. So we will probably go this direction, calling it over OCB mode rather than 802.11 networks. It's the word networks that pose the real problem. Okay, the networks are IP networks. Okay, not yeah. Michelle.
Yeah. Michelle Vetterwald, FB Consulting. So what I would suggest is to take the second one, but change it a little bit. So
okay.
it would be over the IEEE 802.11 in OCB mode.
Yeah. Eliminate the P. Yeah, perfect.
Remove the P because the P is not relevant anymore.
Yeah,
Correct.
yeah, correct. Okay, noted. So yeah, minutes are very important for a meeting. Minutes are very, very important. Okay, so this settled. I will go now to the other questions. The MTU. Okay, when implementing IPv6 over 802.11 OCB, one quickly realizes that we can reuse the MTU that is there for the Ethernet interfaces, and that MTU is 1500 bytes, just as wired Ethernet, and it's just what you use right now on Wi-Fi, 1500 bytes. But wired Ethernet is not 802.11, right? So since wired Ethernet was invented, MTU has constantly growing. You can now send bigger packets on even on wired Ethernet, but also on 802.11. And MTU bigger than 1500 bytes may be useful for example, when an RSU sends a list of point of interests advertised by roadside units, or when there are multiple authentication signatures added to large messages. And there are a couple of other use cases where MTU bigger than 1500 bytes could be very, very useful. So starting from this observation with my colleagues that I listed on the first slide, we looked at what could be the biggest message that we could send on 802.11. So we looked first at the ETSI CAM specifications, which is specific for vehicular communications. And we realized that they specify actually containers or matryoshka puppets, you know, that put one inside the other. So you don't have a size limit. These specifications never say what is the biggest packet that you can send on 802.11 OCB or G5 called otherwise. So we couldn't find a size limit there, and we dropped this direction. Then, we have a person on the email list that suggested that the OCB MTU is 2,308 bytes, which is, almost the double of 1,500. And this is a good news, because if it is so, then we are going to use it this way. This means we will be able to send bigger packets than 1,500. So that's one suggestion. And the question is, should we use these 2,308 bytes, that MTU size that was suggested by Richard Lloyd on the email list? Currently, I'm tempted to, yeah. And then, may I go to the whole reasoning, or you?
Go right ahead.
Okay. So then, of course, we also wonder what do people really send on these links? What are the size of the packets that people really send on these links? So we went asking on ITS Forge, which is an American DOT repository, backed by DOT, if I understand well, repository of open source software and of message parser. And we looked at this, and we saw that BSM unsigned is 171 bytes, 335, 350, and the biggest we could find on ITS Forge was 663 bytes. So this is Well, it will fit really well into MTU of 2308 if we want it. Then we asked in Europe at the vehicular network prototypes that happened last October at the ITS Congress, World Congress, ITS World Congress in Bordeaux, in France, where you could play with self-driving cars that communicate using this 802.11 OCB. And we noticed that they used 108 and the maximum was 524 bytes packet. And that GCDC, which is a challenge for platooning, where people build platoons of cars and they get first prize, second prize, and so on. The biggest packet sent on these links at GCDC was 102 bytes. But of course, this is no IPv6. Now, when it comes to IPv6, there are people at Spain University that have built a CAM heresy as a UDP IPv6 payload. So he had this great idea to send a CAM packet over IPv6, and the payload was only 76 bytes. There were complaints about this being a real CAM packet or some other thing, but well, I take it as 76. And I myself regularly send router advertisements on 802.11 OCB, and their sides are only 125 bytes. So each one of these comes from the experimentation and says that we could safely use this MTU of 2308. But I don't want somebody to come later and that they tell that they need bigger packets, okay? I don't want that. And then there is a question, we can determine the real MTU of these interfaces. We could use PMTUD open source, if such existed. I don't know, I'm asking. Path MTU discovery open source. If we download that, then we can run it on our interface and then we can see what is the MTU of our link. Otherwise, we can write an implementation. It's sufficient to send an increasing size UDP packet until the more fragments of 802.11 gets set. At that point, we know we reached the true MTU size. So this is the ongoing work where we are now. And these are these are the observations that we have made. And up to now, we go to 2308 MTU suggestion from Richard Roy. Yep.
I do not see any 802.11 radio engineers in this room. And those are the people you need to talk to about this. Because the issue is one of congestion. I have seen radio model simulations of a congested roadway where you ain't getting anything through because of the congestion. It depends on, remember those 10 messages per second? And you get 200 vehicles in a crowded, congested roadway. You're not going to get anything large through. It won't work.
Okay.
So you have to be intelligent and seeing what's happening in the airways to understand the traffic to say, can I get 1,500 through, or 500 is going to be a challenge.
Okay.
So
I
look into
understand
that. Talk to the 11 radio engineers. There are simulations which have been done. There have actually been road tests which have been done. I think, I don't know if it was University of Virginia that did some of the road tests on congested simulations. So that's where you need to go to find out what is not just the largest MTU you can do, but what is the effective MTU.
Okay, thank you. Well, you can imagine that I will not go there myself personally. So I'm looking if somebody can help to go there and ask this question and tell us a figure that we must put on this MTU. Okay.
Dan Romashkanu, and I also am the liaison of the IETF to the IEEE Standard Association. This needs to be worked very closely with 802.11, as Bob has said. You'll get help on this, but okay. This will be all this work needs to be in these different phases presented there, and also get a review and feedback from 802.11, and we have the mechanism in place to do it.
Okay. Okay. Thank you.
Jerome Harris speaking, Eurocom. So we have to also go back in time to really think that when they put the 1,500 bytes for wireless LAN, it was wireless, but it was static. So it makes a lot of difference in explaining the fact that here we are talking about a mobile network with a very strong fading conditions and a lot of congestions. And of course, we are here in IP, and IP likes MTUs, but when we look at what we do in ITSG5 in Europe, at least, we don't look at MTUs, we look at the equivalent transmit time on channel.
What's that?
Yeah,
Time on
the
channel.
equivalent transmit time on channel. So I don't care how big the packet is, I need to use the channel for 2 milliseconds. So just increase the modulations, do whatever you want, you can use the channel for 2 milliseconds. So that's something we can do, because this is what we can adapt. But if you tell me the packet is 1,500 bytes, for me, it doesn't mean much, because I can increase modulation, I can decrease modulations. It's undefined for these kind of things.
Okay, sounds interesting. Thank you.
So I think all the prior comments have been really good, and it's good to talk to the radio folks. Vince Park with Qualcomm. But anyway, the other thing I wanted to mention here is that it's also kind of use case specific. So most of the examples that you give there are actually, my guess would be very much driven by the safety use case, which tends to be, all devices sending small messages at some frequency. And so then things like time on channel and congestion and everything starts to matter for the density of vehicles.
Yeah.
But in both the 802 community as well as in what's happening in 3GPP, they talk about other use cases that are non-safety related too. Those may occur on a different channel. And so there may be different constraints in terms of, what's the issue with congestion and time on channel and things like that.
Yeah.
There's also potentially reasons to have bigger packets for non-safety use cases and things like that. So I guess what I'm saying is, don't tie yourself too much just to safety. Generally speaking, as you probably know, because right now, most of the safety applications, people are talking about not using IP. Now,
Yes,
I suspect the heresy statement there might be somebody trying to show that we could use IP.
Yeah.
Possibly,
Yeah.
right? But the expectation right now is that most of the safety traffic will be non-IP.
Yes, it is reasonable to. and we expect-
Before you leave the mic, one quick question.
Vince.
Vince,
Vince.
there's a question for you.
Yeah, sorry, before you leave the mic, a quick one. What are some of those use cases, like point of interest, listing? What are the type of things?
Well, so generally speaking, I mean, obviously you have the old use cases of just infotainment and things like that, but people even talk about just, social networking type services in vehicle spaces. They talk about content distribution in vehicle networks, all kinds of things. And some of these use cases might seem a little bit less likely, let me put it that way, but it's also being looked at, I think, in the industry as these are potential incentives to get somebody to deploy infrastructure that's going to be needed to support the safety applications, right? And so there's maybe a benefit to supporting both in some sense. I don't know if that helps.
Thank you.
Social networking.
Suresh Krishnan. So thanks, Bob. That's a really good point. And I don't mind whatever. So we talk to IEEE, we get a number, put it in there. But the part I'm uncomfortable with, is like what Jerome said, is that if we cannot put in a number, then we have an issue, right? Because V6 assumes a minimum MTU of 1280. Okay. So if we cannot say for sure that 1280 can get through, then we need to specify some kind of adaptation layer kind of fragmentation. And that kind of starts to scare me. Now we are going into 6-LoWPAN, those kind of territory. And we need to find that out fast. Okay. So it'll be good, very soon, we find something like that. And another thing I want to talk about is the restriction. So if you believe that this MTU can be revised up, right? So there's the statement of the draft which says if a RA sends you a bigger MTU, just log it and go away, right? So maybe that's some text maybe you can play with. See, we go with the safe MTU first, and if you get some kind of indicator from the network that a bigger MTU is possible, we can go for it. What I don't really want is PMTUD, okay? Because PMTUD is not reliable on the internet today, okay? It's not because there's any problem with the software or not, but we've seen a lot of brokenness due to people having crappy configurations.
Firewalls.
Right, so it's ICMP based and stuff like that. So people are still talking about whether PMTUD is the recommended way of doing things. You were in 6-man.
Yeah.
The same meeting
But
as
the
me.
PMTUD on a link, just run the same software, but just give the IP
then the
address.
P doesn't make sense, right?
No,
So,
I mean, the software would be called
Right,
DNPW.
so-
Yeah. Okay, yeah.
but, okay, so there is this stuff, there was this proposal floated by Illich, like maybe 2 years ago, like to figure out like MTUs on a link. It went nowhere, but it's probably something you can inspire yourself out of. I can probably send a link to the proposal to the list.
Say that again, village?
Illich.
Illich Van Bremen, okay.
So
Okay.
he wrote this proposal for like figuring out multiple MTUs within a link. Maybe that's something you can look at to inspire yourself.
Yeah.
Okay.
Okay.
Going back to your what IP applications there are, most of them are in the infotainment arena, but there are operational ones. The question of how are CRLs going to be distributed for the 1609.2 PKI and how that will be done. Are the car controls only going to be through the telematics control processor, or is DRC another WAN access method for the OEMs to the cars? These are open questions, not known yet, and so there's potentials there. And many of those will be in low congested situations.
Yeah.
Not where, downtown Chicago when you got other people crying the sidewalks and so forth.
Mhm.
So that it may be, or downtown New York or any other major city. So thus the larger MTUs, if adaptive, whatever, say I can get the big stuff through.
Yes, it would be. It
Yeah,
would certainly be
but the
helpful.
thing is, as we indicate, you're going to have to maybe have you definitely have a maximum. There's going to be probably some reasonable minimum, and everything in between is going to be adaptive learning.
Sounds logic. Yeah. Question, Michelle.
Okay, Michelle Vetterwald, FB Consulting. Just to complete your picture, I've checked on the European standards. We have this geo-networking layer
Yeah, no.
on top of 802.11p.
Yeah.
Oh.
Okay.
Okay, or RCB. And the MTU is set to 1492 bytes.
Okay. For geo-networking.
1492 bytes for geo-networking. Also, regarding second point, regarding your applications, you have listed here, I think it's a very good example, the point of interest. Because you can, for example, we had a standard on the for broadcasting, the list of charging points for electrical vehicles.
Yeah.
And the message could be very large because you have to provide the address, the telephone number, and all sort of information about the charging spot. So we had the discussion in Europe last year, about a year ago, about this MTU problem. And the result was that we are not going to fragment at lower layers, rely on the application to check and to send the correct size of the packets.
Application to fragment.
Yeah.
Okay.
So nothing at networking or lower layers.
Yeah. That's a good point of view at Etsy. Okay, but.
Just additional remarks. This is Jerome Harry speaking. Again on this equivalent transmit time on channel. I know it doesn't work with the MTUs, but I just want to show one thing is that currently, probably some of you have heard that there is a coexistent proposals and the ITS channels in the US and in Europe that is called basically the coexistence between 11AC and 11P or whatever. In the SRC, there will be the Tiger team that will analyze the coexistence possibilities. There was two proposals, one from Cisco, one from Broadcom, one Qualcomm in US and Broadcom in Europe. And one of the proposals was to show that you can only transmit, basically they were saying that you transmit for 2 milliseconds a Wi-Fi system, and then you have to give a small gap. I mean, if John Kenny was here, he could tell even better than I do. But they basically realized that if you want to use the channel, the basic 11 OCB channel efficiently, you have to put regular gaps. And so they don't define it as MTUs, they define in time.
Okay, good to know. We will see how far we can go with that, but yeah.
So this question for Jerome. So is there also a specified rate at which, like you send for X seconds? We can probably calculate back from there, right?
Sure.
Okay.
Yeah. Yeah.
This is I think is a unicast transmission is agreed by SNR.
Please use the mic.
Yeah, sure. It's totally possible. I mean, basically, it's unicast transmission, so you actually get the rate by adaptive race control. So depending on how it is, you can transmit big packets if you have 2 milliseconds of transmissions if you have a good channel.
So basically, what you're saying, Sri, is that with the rate and Suresh, with the rate and with this time on channel parameter, we can calculate MTU size.
Yes.
Yeah, and we could put that MTU. Yeah, makes sense. That's a great idea.
So, and one thing to be, and Suresh again. So one thing to be like careful is like this maximum coupling law. So you figure out like, so with the worst SNR, like what you can do, right? Like, so that should be the minimum MTU that can be supported by the link for you.
Okay, so I'm happy with this slide. We have advanced well. Yeah. And then, of course, when MTU size is reached, that is, the application wants to transmit a packet bigger than what the MTU can swallow, there is fragmentation that is going to happen. That is separation in big packets in small packets. And this fragmentation can happen, can be done by IP layer or by back layer. And here are the three variants that we have: either the IP fragments and MAC fragments too, or IP does not fragment and MAC fragments, or IP fragments and MAC does not fragment. Okay, so you see these are the three possibilities that we need to consider. It's going to be specified somehow. We would like to put it here in this document, although I have not seen other RFCs, IPv6 over foo, that tell which layer does fragment, but it always comes into the discussion. Is who fragments? Is it IP? Is it MAC? Is it? Yeah.
I think it's a very interesting point. Also follow what Michel was mentioning, that we should avoid fragmenting in the lower layers. This is still Jerome Harris speaking. I mean, one thing is important is 11 OCB is based on the 11A. It's not good at fragmentations. It's not optimized as N. It's not implemented. It's optimized as AC. The day we will have a OCB version 2, when we will use the AC capabilities to fragment and aggregate, then maybe it's another question. But so far, it's not a good. I mean, personally, I think it would be not a good idea to fragment.
Okay, MAC may not be a good place for you to fragment. Okay, I can understand. But I think there is place that is planned for this. There are some fields in the MAC layer that says more fragments to follow. So I'm not sure who has fragmented these fragments that are to follow. I will show in a separate packet. Maybe I'm wrong, but.
Suresh Krishnan, I don't think we should have this discussion personally.
In
okay,
the,
like no AD hat.
Okay.
It does not make sense. Okay, so I'll explain why. So there's like an MTU that we pick in this document. Okay, so anything, if you can only transmit smaller things than the MTU, it's the MAC layer's responsibility to take care of that. Okay, so there's no ambiguity here. Okay, so let's say the MTU exposed by 802.11 OCB towards IP is 1500. If it can only send 3 byte packets, it's the layer 2's job to fragment that one. Okay. And if IP gets anything larger than the MTU that's shown on the link, it's IP's job to fragment. There's no ambiguity here at all. So it should be, first one should be like IP layer fragments and or MAC layer fragments as needed. Okay, so there's really nothing to consider here at all. So the MAC layers supports an MTU, anything smaller than that, it's its job. Does that make sense?
Makes sense to me. Although, yeah, as I said also to Jerome, I think there is a field in this MAC headers that says fragment or not, just as there is one in IP. So as there is an extension header, more fragments or no. So I have it all wrong. Okay, so IP does not fragment. Okay.
This is Jerome speaking. I mean, I'm not saying that MAC is not possible to fragment. I'm just saying that from a channel efficiency is not good, because basically every time you have a fragment, you will have an acknowledgement that has to come after the fragment. You have a special diffs that will come after, and this is not efficient in the channel. If you look at AC, for example, you can have a delayed a group acknowledgements, for example, on the whole fragment. This is much more efficient if you are fighting for bits on the channel. So that's why I'm saying it's not efficient if you do this way.
Okay.
Yeah, Suresh again. Like, so I think the point is if you don't want the MAC to fragment, expose the MTU where you don't have to fragment. That's the way to do it. Like, but not having this discussion at all because we don't have a choice. 1280, yeah.
20, yeah, Christian. And the name, please, because
there is a hard limit. Is that IPv6 will not work if you expose an MTU which is fewer than 1300 bytes.
yes, certainly. Yeah. Yeah.
Okay, so because of that, you have the limit case in which you set the MTU to 1400 bytes and you have no alternative
Okay.
but to fragment at the MAC layer when you have packets like that.
Yeah.
That doesn't mean that you
They should be
cannot
put there. Yeah.
optimize your applications to send messages that are smaller than the MTU. That's perfectly okay. So you can have a statistical optimization by the application, but the mechanism must be such that if someone presents a packet of actually 1280 bytes, it actually is fragmented at the MAC layer and it's gone.
Yeah,
So,
yeah. So you raise a good point. We will have to have this statement saying that the MTU should be the IPv6, at least the IPv6 MTU, because this IPv6 MTU is called minimum MTU, and if you expand it, it says minimum maximum transmission unit size.
I mean,
So
you really want to find an MTU that is larger than the minimum allowable MTU.
Yes, yes, yeah, and then at least that we can put. That's for sure. We can put that. It's a limit from IPv6 that should be there. Okay, so at least here we have a good answer. Now we go to frame format. The frame format discussion is a little bit more difficult than the MTU. MTU is just one number, and you have to figure out that number. Okay, but the frame format is has some background that needs to be explained first. What we have put right now in the draft is this courier text here. IPv6 packets can be transmitted either as 802.11 data or alternatively as 802.11 QoS data. And the two formats are expressed here on the left and on the right. You will see the difference. One is 802.11 data, the other is 802.11 QoS data. So we have put this here, but it is obviously a problem because if somebody sends me a QoS data and I can only understand 11 data, the interoperability will not work. So then we went to the implementations and looked what do people use there in the implementations, and we found three independent sources. Okay, so three people who wrote their own software that uses this simple 802.11 data, and we also found one person or one group of people, one whole project actually, using 802.11 QoS data. So I pasted here the details of the formats. On the left side, you have the Wireshark packet capture for 11 data, and on the right, the QoS headers. You will notice at least the difference in size between the two headers. Whereas the left side looks, well, normal, is what we often see on Wi-Fi. On the right side is a little bit more different. Okay, it has many QoS related parameters like priority spare, service period, acknowledgement policy, payload type, user profile summary. These are concepts these fields are not very familiar with, but so there are advantages of each. If you ask me what should I use in my implementation, I will go with what everybody else uses here. 3 independent sources using small packets, and that risk to have more interoperability. Okay, this is what I would actually already use in our prototypes. But when looking at this on the right, well, QoS is a concept that quality of service can be mapped in the channels that are defined by these ETSI and IEEE standards development organizations. So I think this, for example, if you have these channels are defined as being emergency and entertainment. Okay, you have different channels for each of those services that they call. So you could use these headers to distribute IPv6 packets on different channels such as other people do. I will show later. So these are the two basic frame formats that we could use. And I will go to the next slide because the question is, of course, which frame format to use, okay, in order to be interoperable. Because what we put here is that everybody else will use. We want a Chrysler car to be able to talk to a Renault car and so on. So the reasons I said, and I would like to mention an example that was told in the V6 Ops working group, which is that there is a draft called Draft IETF96-ITS-20160721-1400, which proposes mappings of differentiated services call points to 802.11 user priorities for telephony, for multimedia conferencing, for low latency data. So why not for a DSRC control channel? Okay, this is the obvious question that would go more into the direction of using IP on any channel of DSRC, but this is a question that comes to which frame format to use and to write. So that's the question for the group. Yep.
Okay, so this is Jeremy speaking again. Here you talk about a lot of different things. It's a bit complicated to address them, but one thing is that QoS is seriously misleading here. Okay? It's seriously misleading here. It's not the QoS as you understand it in cellular networks, okay? A wireless LAN doesn't provide that kind of QoS unless you really want to be an access point that is controlling everything. Here, it's about having the different queues, EDCA queues, all right?
Okay.
And this is mandatory in 11P.
This is?
It is mandatory.
Mandatory?
Yeah, if you take the 11P specification, you have to have 4 EDCA queues. It comes with.
We didn't see that in the OCB tutorial.
Yeah, but the thing is, you have a lot of experimental work that you've been doing, extending some existing wireless LAN systems. So it's okay. But basically, if you use a ITSG5 DSRC systems, then you use, of course, the 11 OCB, and you automatically get 4 EDCA queues that are adapted to the specific channel configurations.
Okay, so basically, you're saying we should use on the right.
Well, I mean, if you don't want to use that, then you have to talk to IEEE. We're not the right person to talk here.
Okay.
That's the point.
Okay. This is the second matter one should ask to IEEE. Okay.
Yeah, I mean, basically, we don't have control on what we do in that.
No, but I mean, whatever they do, we should decide to map on we decide the mappings. Okay, if there is some mapping, the code points. Okay, yeah. DSCP code, but this is an IP term.
But then I'm still not totally sure what's the problem actually here, because
I mean they should be interoperable.
No, interoperable is one thing, but while we are talking about small bits that tells you the traffic class. I mean, EDCA queues are quite useful if you want to differentiate the different types of traffic, and it is part of the standards for in Europe and in US.
Okay, IP also has flow label and traffic class.
Okay, I think the area director really needs to say something.
Yeah, sorry, Jerome. I understand your point, right? But the point is like, in the IETF side, right? When we specify IPv6 over FRU, we need to specify how the IP datagram is mapped onto something on the link layer. So there's like 2 ways of doing it. Even in Ethernet, we have like multiple ways of like putting a frame format, right, on the wire. So he's just putting up 2 choices. I don't think he's actually trying to define anything in this. At the end, like whatever is going to get defined is whatever's in the IPv6 header onwards, and then how the IP addresses get mapped into the link layer addresses. That's all within our scope. Okay. So how is a unicast address mapped into like a link layer address? How is a multicast address mapped into a link layer address? And how is like an IP address formed on this link layer? That's pretty much within our scope. We cannot change or redefine some frame formats IEEE does. I agree, but I don't think that's the intent of this. The intent is to say like, there's 2 ways I can map this IP datagram onto 802.11. What does the working group prefer? That's what I understand Alex is asking.
That's correct. That's correct. Yeah. For this one.
So I'm Vince Park.
Vince.
I'm going to say some stuff that I have partial knowledge of. So feel free to correct me if somebody knows better. But effectively, I think in the 802.1609 specs, they've already defined how the wireless, the wave short messaging protocol, as well as IPv6 map over top of the lower layers. And so part of what they did was use the snap header, which is an LLC layer header within IEEE, which I think might be your one on the right. I'm not sure.
It's not here now. I mean, many people write many things. Okay, snap is not here.
Yeah.
This
but-
is deployment.
Right, but in the snap header, you do have a type field that identifies what's above it.
Correct.
Right, what protocol is being carried, and they have a different type,
Okay.
protocol number for WSMP versus IPv6.
Okay,
So they've
so we
already
should,
defined one, and I guess I'm just suggesting we make sure that we're not trying to change what's already been defined.
no. Okay, if there is, let me say quickly, if there is a snap header that I did not find on these dumps, okay, this would distinguish between the two frame formats, and depending on this we will write down that depending on the value of the snap, we will use this frame format, the QS, with DSCP mappings, or this other format, okay? This is what we are going to do. If I find this snap,
I'll take a note to ask Dick Roy, because I'm pretty sure he's the one who's the person behind this. The link layers is there in both of those. The Ethernet header is there in both of those. I think if I remember right, and Dick will slap me across the side of the head on this one, that the one on the left is the basic, okay, I have the ether type IPv6 and I do that. And as Jerome mentioned, you're going to be put in a particular performance queue, because what is DSRC for? Safety. You got a safety message, it goes out before anything else. And you got safety stuff queued up, everything else waits until the safety stuff gets out. What the one on the right allows is that I got some IPv6 stuff, which is potentially just as important as the wave messages. So I can fit myself into the wave queues and do things with those particular quality features. So it is then up to the various base stations to work with it. So thus it may well be that we'll be specifying both of them for different classes of applications. I will check with Dick on this, because I believe he is the culprit behind it.
I don't think that's right.
You don't think it's right?
I think that's not in our charter. If you're running wave over top, somebody else has to figure out how to map wave onto IPv6.
No, it's IPv6 over wave.
No,
we don't do that.
we don't do it.
Fine. Then you've done the one on the left.
Got to re-charter to do it
Okay.
would be a more correct answer.
And then I'm
Okay.
almost sure you're the one on the left, not the one on the right.
Okay, okay, noted. So if no, yeah, this may be because of it being, even though if you look at the headers, Wave is an application, but yeah.
No, it's
Well,
both.
It's a different use of the net application.
Okay,
It's a demultiplexer. We're only dealing with the right-hand side, or the IPv6 side of the demultiplexing, not wave.
Wonderful,
They have different ether types.
wonderful.
And Alex, not to rush you, but
Yeah,
I want to
okay,
give you a
I'll-
time warning.
but hurry up.
Unfortunately, now we go in the area that we have not up to now produced anything, but we will write the text according to the implementation. So the interface ID, how to generate this interface ID, this is a huge other discussion, but we have no text for the moment. Address mapping, unicast also work underway, should be straightforward. In this, actually, we decide how to make a parameter to how to make the option link layer to neighbor discovery messaging. And it is straightforward. There is nothing new here. So it's just copy paste from other drafts. It's nothing special. In multicast, there is a question. And this will close if I need 5 minutes to present this. Typically, when you say IPv6 over 802.3 or 802.11, or you map the all nodes multicast address with link scope to a MAC address that has this form here, starts with 33330001. Okay, so basically you map any identifier here like 1 into 3333 something, like FF02XX into 333XX. So you may wonder, what is this 333? And after digging a little bit, we have found that this is another historical matter that is not assigned at IEEE, but it is only considered by IETF IANA. And it is a local address. It is not a globally administered address, it's a local address. Now, what other people that run Wave suggest us to use as the multicast address is to use this FFFF all broadcast address. that is commonly used in WAVE, in HCG5, and in IPv4. So they are also telling us, we are using it, please use it also for IPv6. Now there are global addresses for multicast that are reserved. For example, this one, 0180C2, is reserved by IEEE for what I believe is ISIS. And there is a 01005E address reserved for multicast address for IANA. And this is a global reservation. It's not a local assignment. You can see it in this bit, 1 bit. So we could continue using the 333001 address as just like IPv6 over Wi-Fi or IPv6 over Ethernet, or we could think about using this IEEE multicast address that is considered to be unique. Okay, there is guarantee of uniqueness, whereas for this there is no guarantee of uniqueness. There could be how to say there is a risk of collision for 3333. So the question is this: which one to use? And up to now, we consider using this 3333001.
Yeah, quick. This is Dino. Quick comment on the multicast addresses. There's a lot of hardware that's built that when it sees a destination address of 5E, thinks the encapsulated packet is V4, even though it should look at the ether type. So you could run 86dog inside of 5E, and it could work for this case. But just want to let you know, there's a lot of
this one.
Yeah, there's a lot of broken implementations that assume 5E is IPv4.
Okay.
It's just a destination MAC address. You should be able to receive it, and then you should demux on the ether type field saying 86dog is IPv6.
Yeah, this is what.
But not a lot of existing hardware that probably won't be put in this environment. But just to let you know.
Okay, so this gives more insurance to.
I would
to
suggest
use
using 3333
to
because it's more standard.
Or to ask for a 5F for IPv6. I don't know. Yeah. Okay, because 3333 is not allocated at IEEE. IEEE doesn't know it. There is risk of collision. Yeah.
Brian Haberman. The advantage of using 3333 is that you get a full 24 bits to map addresses in, so you reduce the amount of collision that you potentially have. Very important. Thank you, Dino.
And Alex, we're really out of time now.
So this ends my presentation. If the last slide you will read, there is something about Uber taxis on it, but you'll read it later. So thank you for attention.
Thank you. Thank you. While I prepare the slides, the blue sheets, I have one here. There's people probably who didn't sign. Where's the other one? Okay. And Jerome, I think you're up. Perfect.
Okay, so this is Jerome Harry. I'm going to make a complementary presentations to what Alex was presenting before, related again to two other aspects that we discussed in this ITS domain for transmitting IP packets, IPv6 packet over OCB. And this is cooperation also with Alex and also Christian. So here, we're also very happy to be able to come to this concept. So a few things I just want to briefly remind. I see it's partially already covered, but as we don't have much time, I will just go very quickly on that. I just remind the fact that if you have a wireless LAN, you have several steps before you can actually communicate. So you have the scanning process, you have an access point that have a beacon, then you synchronize. I'm apologize for switching these two. Then you authenticate, associate, communicate. If you transmit with OCB, basically everything is almost gone. You do not have synchronization. Synchronization is up as an upper layer perspective. You can actually have some special additional messages if you want. You do not scan, so that's very important. There is no scanning process, in the OCB phase. You assume a well-known channel. I'll come back later on that. We do not have authentications. It's supposed to be a higher layer authentications. We have to do something on that. Implicit association and direct communication. So this actually poses a bit of problems if you have to use IPv6 over this OCB mode. But first, I would just give a brief scenario here, because here, just to be sure that we don't address or that even what I said might not go in the wrong directions. First of all, I do not look at what I'm going to say today for anything else than non-safety related traffic. So I'm not going to address safety related. This is as most people were saying, non-IP transmissions. We also look at the single hop IPv6 communication. For everything that's related to multi-hop, we have to go to our Manette colleagues. They're also working with, on that for many years. Vehicles may have multiple IPv6 things, and vehicles may not always be connected to a internet connection. So it could be also totally disconnected or partially connected. And eventually, IPv6 may coexist with non-IP stack. When I mean non-IP stack is the safety aspect. So 1609.1609 or the GeoNet system, or maybe not. And in very important aspects, if you are a car and you are having your engine turned on and you are actively taking part of traffic, then you will automatically transmit non-IP traffic. So either 1609 or HCITS traffic on the channels 178 in US, 180 in Europe. So whatever you do with IPv6 shall not break any non-IP mechanisms and shall not create any interference with non-IP traffic. This is very important. What I mean by non-IP mechanisms is anonymity, for example. We have pseudonyms, and creating interferences with non-IP traffic is what we discussed before, congestion. So these are a few, I would say, challenges that we try to list of what we would like to discuss in this group. First is a scanning mode. So it was partially discussed before. If we don't have a scanning phase in OCB, we assume that we go to a well-known channel, which was to be called control channel in the past. But the problem in both standards, ETSI and 1609, the control channel is blocked from IP traffic. You cannot use IP traffic on these channels. So which channel are we going to use? We have to find a way for announcing where we are going to use the OCB system. So we need a service announcement process. It exists in GeoNet. It exists in 1609. Now, if we use IP, how can we announce it? It could be interesting to think about that. Then security. If we don't have any security mechanisms, basically we have an RSU that is there. You transmit a packet. It's not going to check who transmitted it. It's not going to check if the packet has been forged on the wireless link, and this could go to internet. And if you are two cars transmitting one to each other with OBUs, no one is going to check if the one transmitted the packet is actually the one who transmitted the packet, because the Wi-Fi authentication mechanism is not activated in OCB. Then very important aspect, and I think we had a long discussion also with Dick Roy, we have to define this OCB link. OCB link is strongly asymmetric. So basically, first of all, you have different antenna heights. The RSUs is 20 meters height. The cars is 3 meter high. So it's possible and it's highly likely that a car will be reached by an RSU, but the RSU will never reach the car. And the car will never reach the RSU. So we have to be sure that if we are using IPv6 on this kind of link, that the IPv6 can work. And there are some extensions that we can look at to get inspired, but it's something important to keep in mind. IP addressing and privacy is also important, because now if I'm moving around, we cannot keep our own IP address. We have to change it once in a while, otherwise we can be traced. Well, I know already the debate. Some people might say, well, I'm traced already on Facebook, I don't care. Fine, but from a legislation perspective, we have to also have the mechanisms to change the address, change the prefix, such that once in a while, it will be hard for people to trace us. And that is typically things that we have to look at.
Can I ask a scope clarification question? It's related to your slide, but it's also related to something that our chair said earlier. I guess the issue that brought it to my mind was when you were talking about the control channel kind of operation. And in 1609, they did define kind of control channel operation mechanisms. And of course, then you could set up one of the channels to do non-safety application and run IPv6 over top of it. So, sure. So it still ends up being used as a transport for IPv6. Yep. And I guess what I'm asking is that part of the scope that you're trying to, in a sense, redo that work without relying on 1609? And that's why I mentioned you, because you said we're looking at
Could be.
IPv6 over 802 OCB, but not over wave. And to me, there are those wave pieces related to control channel operation, to security, and even some MAC layer changes that the 1609 group drove into, 802.11 or is driving into 802.11. And so do you see yourself as defining the IP parts of the IPv6 stack in the typical wave picture? Or do you see yourself as throwing away the wave stuff and doing something in parallel?
I think it's very good questions and clarifications. So there is a disclaimer later here that says that, of course, if we have these mechanisms and we can use them, then we should. But the thing is, we have to know how, because we said we don't use wave. So if we don't use wave or we don't use geo-networking, then it's not clear about the interface. How can we use these mechanisms if we don't have the architecture to do that? So that could be a first step, to look at how to use these mechanisms if they exist, because I do not claim here to reinvent the wheel. So very talented people spend years in defining them.
Russ Housley speaking as individual, which is why I came to this mic. So I think we have to pay attention to wave, and there's text in the charter that talks about coexisting. So we don't want to depend on that stuff. And that's what I was trying to say earlier. Maybe I didn't say that as well. Hopefully I said it better right now. But in this privacy stuff, some of the things that are going on in 1609.2 are changing your MAC addresses periodically. So if there's a related change in your IP address, these things need to be synchronized. Because if you change them not at the same time, then the one that didn't change becomes a way to link to the one that did.
Yeah, no, that's absolutely true, and that's the complicated aspect. We have to be to look at what the other stack do.
I think it's actually 1609.4 that calls out the random MAC changing, which 1609.2 takes advantage of. But yes, it's the MAC address is regularly changed. And whatever you do, basically expect that the MAC address is frequently a different MAC address.
Yeah.
Russ Housley again. I would not describe it that way. Takes advantage of, provides authentication of.
So, and I also like to say that in the ETSI and in car-to-car in Europe side, they also do that. So basically, we have active stacks for safety-related mechanisms where this is defined and enforced. So one question, one action we could do for this group is to try to say, well, we are aware of this, and let's see whether we totally ignore it. This is a strong statement. I would not support that completely, but I would say we ignore that and we define something that is doing the equivalent in different ways, or if we find a way to reuse them, even if we are not using the stack. Okay. So I will move a bit faster because we're also looking, we don't want to take too much time. So then here, I think I don't need to go too much details here. I will just try to show one thing is then 1609 and also geo-networking, conceptually speaking, all these aspects require a very strong architecture. We have the public key infrastructure certification authority that goes up to the national and European level for Europe and national level in the US. This is something that is heavy. And the reason why they need that is because as the vehicles do not need to authenticate when they connect to the Wi-Fi system, they have to be pre-authenticated, so to say. So they have a set of certificate, public key, private key combinations, plus anonymity, plus a lot of pseudonyms, and all of this has to be preloaded and recognized, authenticated by a public key infrastructure. This is something that is quite heavy, but they do that because we are talking about safety-related communications. Now here we are talking IPv6. We might do safety-related communication. We might also do a bit light-weighted applications that might or might not need that heavy communication systems. Nevertheless, this is basically how the system is done on 1609 and geo-networking, even though that the name might differ a little bit. And we need the public key and private keys to do authentication. We need also that for encryptions, even though that for most of the communications on, at least at ETSI geo-networking, there is not that encryption. But also it adds actually overhead, because if you have to transmit basically your signature and your certificate for every packet you transmit, which actually we don't do all the time in Etsy, not specifically because of overhead, but because of the, I would say, computation capabilities on the vehicles. This adds also overhead, but this also requires an extension to the packets, which is specified in geo-networking in 1609. When you have the specific message, you have, of course, your pseudonyms, you have the signatures and the certificate transmitted in theory for every message you transmit. So this is something we also have to think of how we can do that later. Okay, one thing we proposed in this draft was to try, if basically we do not use the 1609 or the geo-networking anonymization system, then how can we provide the anonymity equivalent for our IPv6 solution? So the proposal was to have an address anonymizations, where we basically would like to avoid that the identifier could be tracked either by the MAC address, the IPv6 prefix, or the IPv6 host identifier, because it's quite something that's quite easy to follow. Even in some of the IPv6 mechanisms like neighbor discovery, it's also something they can learn a lot of things about the neighborhood. So it needs to be randomization, but as you were saying, it has to be synchronized. We cannot simply randomize, we cannot basically randomize. Randomize means what? Changing an address. So if we change our address, we have to be careful when we do that individually, but we also have to be careful when we do that in cooperation with the other stack, because basically, first rule that I mentioned, IPv6 shall not break any mechanisms of the non-IP mechanisms. And that is very important.
Timing warning. Can you speed it up a little bit?
Well, that's basically that slide. So we want to find a mechanism to change the random ID and perform change at the right time, so to say. I think maybe you want to say a bit more?
Yeah, basically, one very simple way to do that is to follow RFC 7217 for the generation of the IPv6 address identifier, using the MAC address as the stable key. That means that each time the MAC address changes, RFC 7217 tells you how to build the IPv6 identifier. Mm-hmm. And that gets you a specification which is aligned with all the other standards.
Exactly. Thank you, Christian. Okay, last slide. A few proposals, but again, big disclaimer. Disclaimer means that if a vehicle is having access to the stack in one way or another, then we should try to use them because they are there and they are usable. So it could be nice to try to use them. If we do not have access to them for any reason, then this is the purpose of today's draft. The randomization, as described by Christian before, and I also wanted to add the second aspect, which is security, because randomization of the ID is one thing. We still have to add authentication at least. And the problem is if we don't have predefined keys in vehicles, how do we do that? So there's a couple of existing specifications that we could use. We could use, IPsec could be something usable, but it is very strict, and we need a mechanism to share the secrets. There is other RSA approaches in the RFC 3971, even though that is not really used, as I heard. But nevertheless, it's important to discuss a bit that, because if we cannot authenticate an IP packet that is transmitted, then we have a security problem.
Well, I must say that there is a reason that SAND is not used anymore. And the reason is essentially that when it comes to cryptography, the 64 bits of the IID are a small number. Mm-hmm. So it doesn't provide you a whole lot of protection. And it brings you a lot of complexity. Mm-hmm. If you want to make the 64-bit into a strong identifier, then you need effectively to make this 64-bit a solution of a cryptographic puzzle. But then that's not something that you can use with sensors and things like that. It requires way too much computing. Mm-hmm. So I don't think that we should go there. Okay. It's better to say that if you want security, you have security with a certificate, you authenticate the message when you send them. Mm-hmm. What you're trying to protect otherwise is just protecting against denial of service attacks. Mm-hmm. That at the low level, people try to deny you, but frankly, that's not worth it. Mm-hmm. because it's so easy to deny service over wireless. It's not even funny. So it's so basically, I would say we put the security at the application layer using the certificates, and we do something simple at the IPv6 layer.
Okay.
So Krishnan, so I agree with Christian, and there's also like a sec parameter inside CGA which can give like some kind of extension to this bit length, but I agree with him as like an overall point. I don't think this is the right way to go.
Okay, so basically, if I understand well, all the authentication aspect will also not be done there, it will be done at the application layer.
Yeah.
Okay.
Thank you.
Next.
Paul? And Paul, you have quite a number of slides. If you want to try to go through all of them, you have like 3 seconds per slide. So I would suggest you prioritize what you want to speak about.
Okay, sure. Hello, everyone. Okay. My name is Jeon Porjeon from Sungkyun University in South Korea. So we have a limited time. I just address the observation from this survey rather than list up all the papers. So this is a collaboration work, the Sandra, Nabil, and Jeremy. So the objective is we want to survey the current state of art, the research in academia to working for the IETS group. So our assumption is the L to the 11, the OCB mode, it is called the 11P, consider the MAC protocol. Also, IP version 6 is considered the network layer protocol. So load sign unit and some sort of virtual cloud is called the traffic control center can be used. So this survey consists of 4 categories. The first one is address auto comparison. The second one is the network architecture. Third one is routing. The first one is the mobility management. So the address auto computation case, we have 3 papers. The key observation is we can auto configure using DHCP style, such as the cluster leader can allocate the address, or we can using the physical geographic location as IP version 6 prefix. Lane and road segment has unique IP prefix. Otherwise, we can use a geographic region as IP prefix. And also, we need to consider IP version 6 enable discovery, because the link concept IP version 6 is different from the wireless network because of the mobility and over the topology of the vehicles. So we need to take care of that. Also, the rapid DAD also should be considered because of vehicle moving fast. Also, we survey the network architecture papers, 7 papers. The key observation is the unidirectional links exist because of the directional, the power control, and also some interference. So this is also different from IP version 6 link concept. Also, control plane and the data plane should be separated, especially DTN case, we need to separate. And also, providing some security for the vehicle IP address. We can use random or pseudonym ID can be used for the IP address. Also, IP tunnel should be minimized or avoided. And also, the vehicle do not have a home network, so especially DMM approaches case, we try to decentralize for network management, mobility management. Also, protocol-based mobility case, avoid the mobility to the vehicle as a mobile load. Also, IETF architecture, we can consider the terminal leaf node is a vehicle, and also relay node also can be advantage 2 hop or 3 hop away for multi-hop. Also, internet vehicle providing the access to internet connectivity. The third one is the routing. So we also survey the routing. The key observation is the IP auto configuration is the prerequisite function should be performed efficiently, and also keep in mind the vehicle the add-on network case. There is a lot of the network fragmentation and also merging during the travel of vehicles, so should be considered. Also, neighbor discovery consider this network fragmentation. Also, again, IP version link concept also should be supported by sort of the geographic routing. And the mobility management, a lot of paper, 7 papers. The observation case, we can using the PMIP plus DMMN, or we can using the NEMO based the approach plus proxy mobile IP. So also the interesting part is SDN can be used for this mobility management. The summary of this survey, IP version 6 over the wave, such as L2.11, the OCB mode is good for the non-safety application. But however, the navigation case also providing driving safety, providing some the blind spot case. We can show the following vehicle. So still we can providing driving safety, also navigation, also supported by some real-time traffic congestion information from roadside unit. We can also take advantage for efficient routing, the driving. Also infotainment. Also neighbor discovery case, we consider high mobility, also network fragmentation. So also IP version 6 link concept should be considered. Also address auto configuration case, we consider the rapid mobility scenario, the DAD also considered. Also infrastructure can proactively perform DAD for the sake of the vehicle. Also, routing and the mobility management case, you can see the vehicle following along the roadway. So the mobility prediction is more suitable instead of comparing with the mobile add-on network. So we take advantage of the predicted mobility for the routing and mobility proactively. So next step for this draft, many people suggest transform the survey paper into taxonomy. So our authors consider taxonomy, and also we advance our draft, including the several security papers, and also we including more paper. So as you can observe, many people the input good relevant papers. So our authors also include that paper. So also we consider the include the industry activities such as Toyota and Honda and Hyundai, other automotive company activity, also the standard organization ISO and the HG, etc. So this is the reference papers. So if you have a question and a comment, please let me know. Thank you.
Thank you very much, Paul. And Dino, I don't know if there's going to be enough time for you to present, but at least if you want to come up and advertise the presentation that you're going to do later. We have about 10 minutes, if that's enough.
I'll try. Yeah. Here you go.
Almost no more time on channel.
Okay, so I'm going to give this presentation in about 1 hour in the Lisp working group. So if we have to rush through this or I get cut off, just come to there. This is a possible solution for mobility, IP address mobility. So problem statement. Mobility problem is simple. When the EID moves, you send packets to the new location. When I'm referring to an EID here, I'm talking about an IP address of the moving entity. Okay, let's speak as endpoint ID. Well, mobility really isn't that simple. And the reason it isn't simple is because packets are already in the network and they're going to the old location, even if the EID is no longer there. So that means packets are going to get dropped. And if the EID moves to the new location, until the sender knows about where it is, it's sitting there not receiving any packets. So this is a pretty hard problem. You can't make this stuff happen autonomously. So if anybody tells you that they can do mobility with zero packet loss, they're totally lying to you. Because if you use mobile IP, you have suboptimal routes and the opportunity of drop packets is greater than otherwise. If they say they're going to be able to queue packets in the network waiting for the thing to arrive, the queue is limited and finite, so packets are going to be dropped anyways. So there's really no way to do zero packet loss. But maybe this is a way. You guys judge. This is these solutions are not make before break. In other words, what happens is when an IP address moves, signaling is done, and therefore that's where you know the new location. If you have to signal when the move happens, you're going to have to drop packets. You have to do this stuff a priori. So how do you know where something's going to move to? Okay, so mobile IP, these are struggling solutions of the past that couldn't do mobility very well. You can't send to a home agent because it doesn't know where the new location is. Plus, the previous speaker said, why should you have a home location if you're always moving? So tying address to some anchor point that could be very far away is probably not a good thing to do. Inject host routes. Well, that's a lot of state. It has to propagate everywhere. There's going to be all kinds of filtering policies where host routes won't work. The point is that the old and new location are at the same time in the network because you can't drain the network of the address and then re-advertise it. So you're going to be sending packets on routes natively throughout the entire network to the old place where it's not going to be. In some places where the new route has come, you'll be redirected to the new place where maybe the EID hasn't arrived yet. Okay. Handoffs are slow because the EID host route has to go everywhere. So the most promise is using a locator ID separation solution. And it's good if signaling can be fast. But if you signal, it's not make before break. So we really don't want to drop any packets whatsoever. We want handoffs to be instantaneous or atomic. Good luck with that. We're going to try. The future is clear. That means we know where we're going. Okay? What if we know the new locations? What if we assume some directionality of the moving entity? Let's have the source sent to all of the new locations. We'll search and find where the EID has to roam. We don't have to search and say, oh, it's there, and I'll keep sending it there, because once it's there, it's going to move again. So what we're going to do is we're exercising a bandwidth signaling trade-off. We're going to waste a little bit more bandwidth so we don't have to signal too late. Okay? The idea is called predictive RLOs. A routing locator in Lisp is where you encapsulate to. Okay, and so these are going to be roadside units running Lisp XTRs. We don't have the encapsulation overhead on the radios because the packets will go natively from the XTR to the moving entity. Okay, so let's say in a mapping database, you have an EID that's registered as an ASCII string called Main Street. And let's say it's called RLOC A, B, C, and D, going down along the road. And let's say EID A and EID B are on that street. So they actually point to Main Street. So it's a little indirection in these table entries. Okay. So what happens is the server far away that wants to send a packet to this moving entity will basically send it to this replication list. It sends it to all of them. Packets will go to all three. A unicast packet is being replicated and encapsulated to all 4 places. Because we don't know if EID-A is at A, at B, C, or D. So what happens is, in this case, when EID-A is sitting over here at A, the packets are going to go to B, C, and D. It doesn't know that A is directly connected, so it simply drops the packet. XTRA has discovered the EID because it's either send packets or done signaling. There's many mechanisms to discover that, and then therefore forwards it locally on the LAN or on OCB or whatever the case may be. So the XTR replicates to RLOCs, and the packet arrives at XTRs. If the EID is discovered, the packet is forwarded, else it's dropped. Now what we can do is, B is over there at XTRB. Now what happens is we can optimize and reduce the flooding overhead. So if a packet is encapsulated back from B to S can say, oh, he's already passed A, and now I just have to replicate to B, C, and D. There is no signaling here. This guy's got a map cache entry on where he's going to replicate to. And all he has to do is, when he sees something, is change one forwarding entry local, a local decision, to say to go to B, C, and D now. We can also use geofencing to decide when to replicate and when not to. But my watch just told me I have to stand up. Okay. Okay, what about an intersection? This is kind of cool. We have directionality, but we may change direction. Okay, so while we're going straight away, we have this thing called Main Street. We're replicating to ABCD. You see ABCD, but you see those 2 RLEs in the middle? That means you might go northbound and take 1 or 2, or 1 or 3, or you may go southbound and take 2 or 4. How would you do this sort of thing so you can kind of predict the direction you're going to move in? So if EID-A gets close to the intersection, in other words, close to B, this is all sitting in that remote encapsulator. It can say, boy, now it's at B, maybe I should be replicating to 1, 3, 2, and 4 all at the same time, because I don't know where he's going to move yet, but I'm getting those packets there, okay? Once he makes the decisions and comes down here, you can stop replicating to the top. This is all done by a local decision in the encapsulator. No signaling, 0. It has to be done locally, or we're not going to be able to deliver all the packets we can. Yes, we're delivering packets everywhere else, but we're trying to optimize at a later time frame than we're trying to deliver packets. No protocol changes to Lisp to do this, by the way, because we just leverage off the multicast capability that's already in Lisp. And we use this new type of format called an RLE, a replication list entry. And multicast just works because it's a multicast solution, kind of. Quick demo. I did an implementation of it. Okay, this is an example where 2222 is the moving entity. This is a registration in the mapping database. This is the RLE down at the bottom. So the roadside units are 1, 2, and 3. This shows you an example that the ITR has the 222 in its map cache, so it has that replication list entry. It's showing that there's a packet going from 1 server to 2. And it shows that it's replicating to 1, 2, and 3, getting it to all the places. If you already have a Lisp multicast implementation implemented, it takes very few lines of code to do this. And this is without future work. So this is an internet draft that's in the Lisp working group, but it's an individual submission, has not been accepted as a working group draft, and we're presenting this for the first time now.
And we're out of time.
Okay.
Thank you.
Don't take the questions, we'll do it offline.
Thank you, Dino. Appreciate it.
Thank you.
Thank you.
All right, so now, Suresh, the room is all yours.
Okay, thank you. So thank you very much. That was a really nice meeting, and it gave like a really good understanding of the problem space, at least in the IPO or foo space. And so, like for next steps, right? So, so I would like you guys to like finalize the charter. Like, so looks like it's almost there, but do you want any more time to finalize the charter before I ship it off? Okay. So probably just provide like a comment period, like for people who just saw this thing for the first time, maybe a week or something. And then I put it up for the IESG. Okay. And then we figure out like how to go about from there. So there's like a next telechat we can possibly take a look at. This is the 18th of August, right? Like, so give people a week to comment on the charter, and then we can take up the discussion on the list. Okay. Thank you very much. Thanks all for coming and for all the effort you put in. Thanks.
Thank you. Blue sheet. Wonderful. Thank you very much, Ross.
Yeah, no.
Yeah, no, if I don't do it tonight, I'm not gonna be for 2 weeks. That's right. Yeah. Excuse me. Thank you. Sorry for the reach.
Thanks for chairing the meeting.
Absolutely, absolutely. Pleasure. Thank you.